alkanes and the alkynes all together. So the first thing you could do is substitution reaction. For substitution, you need an alkane. That's the only reaction an alkane is really going to do, minus a combustion and cracking. So those are single bonds between carbons, all hydrogens are on the side. So hydrogen 1, 2, 3, 4, 5, 6, but I'm not going to draw them. And what will happen is if you introduce a halogen, so Cl2, that could also be bromo, iodo, or fluorine gas as well. What will happen there is that one of the hydrogen atoms will substitute its position with one of the chlorines. So the new product is a haloalkane. And the side product is H with the other chlorine atom. Then there's cracking. Cracking occurs under UV light for long molecules. So if I had something like that, like a 9 carbon chain, under UV, I would always make ethene, always. And then whatever I'm left over with. So if that was 9 carbons to start and I subtracted the 2 for ethene, I should only have 7. 1, 2, 3, 4, 5, 6, 7. So those two aren't so bad. And neither is the alkenes, alkynes. It's just actually the same reaction over and over and over. You're just switching the thing that you're adding to it. So let me show you that. So for the addition reactions, you always need that double bond or the triple bond because an addition reaction requires you to break that double bond and form new bonds to it. So you could add H2 across that double bond. That's your hydrogenation. You could add Br2, like a halogen, that's your halogenation. You could add an H and a Br, HCl, HI, like all of the halogens could be with an H there, and that'd be your hydrohalogenation. Finally, you could add water, and that would be your hydration. But every time you're going to break that double bond, your carbon's going to be left like this, but you know carbon requires 4 bonding pairs. It requires another bond, so that's why it is H to H. One of those H's sticks here, so that this carbon has 1, 2, 3, 4 things, and the other H will stick here. So it has 1, 2, 3, 4 things as well. So from substituting an alkene with H2, you're just going to make an alkene. If I wanted to do that with the this should be Br2. If I wanted to do that with the Br2, I would have that. And this time, Br adds one to Br over here to that carbon and another one to that carbon over here. So this one gives me a di-substituted bromoalkane, which is different than the alkane substitution reactions, and I used to get those ones confused. You just have to remember that the substitution isn't breaking any bonds, so you don't have to add 2 things to each carbon atom. There you're only just switching a hydrogen and a halogen, but here because you're breaking a bond, you need to satisfy both of those carbon atoms again, so that's why you add both of the bromines. So hopefully that helps you with a better understanding of it. So for these last two, the hydrohalogenation and hydration, because these things that you're adding are not symmetrical, like I'm adding a H somewhere and a Br somewhere, and I'm adding a H somewhere and a OH somewhere here, these two are Markovnikov's rule. But this isn't an example where it matters because both carbons here on the left and right only have 2 hydrogens each, so you just decide. I can throw the H here and the bromine here, and in this example, again, I could throw the OH here and the H there. So I would be making an alcohol for a hydration reaction and another haloalkane for the hydrohalogenation reaction. So now I'll show you an example where Markovnikov's rule does matter. And for that to be the case, you need to have different number of hydrogen atoms on the carbon atoms with the double bond. And what that means is that there has to be like another carbon atom here, so that this carbon only has one H, but this carbon has the two H's. So pretend I added something like water here. Think of it like H and OH in your head, and the rich get richer. So my major product will be adding the H to carbon 1, because carbon 1 has two H's already, which is richer than carbon 2 only having one H. So there's that H that I'll add to the two H's that existed there already. And that H is from that water molecule. This carbon has an H and a CH3 already, and it needs another bond, so that's where the alcohol comes in, the OH over there. That would be the major products for this reaction. And I only want the major product on test, but just FYI, the minor would be the other way, where the alcohol group goes on that carbon 1. And that's really it for the reactions of hydrocarbons.